Alright guys, how you going? I just thought we should do a quick on the physics of it. I haven't actually got any qualifications, so I can't tell you about the physics of it. What I can do is show you the books, and then you can go and you can either get the books, get access to the books, or whatever. This would be one of the first books that I would buy. Or get my hands on. Really great author. He goes through, he explains everything in layman's terms. So this book relates mainly to the top of Holtz machine that we're using there to generate the potential difference. And he explains it in layman's terms. He's really good. He'll help you understand how to fix leakages and all that. Once you get with this stuff, once you start getting over 40 or 50,000 volts, it's very hard to contain it. It becomes like a gas. The higher in the voltage, the more pressure in the gas, and it just leaks out of everywhere. When you turn the lights off, you'll see it going everywhere. It sprays on everything. And it's constantly trying to balance itself. So anyway, he gives you a really good insight into static electrics. Now, they went away from static electricity a long time ago. Which I think was a bad move, but anyway, so that one there, AD More Electrostatics, that highly recommended. The next one would be this one here. Again, it's an electrostatic book. It's pretty good. He deals in a much higher voltage. He gets up to 200,000 or 300,000 volts. It's counter-rotating, so I didn't do counter-rotating for a reason. The reason being you only have two surfaces available to you. You can engineer it so you've got multiple, but you better, you've only got these two surfaces, so unless you've got a really big area, you're limited to what you can do. When you stack it like this, you're getting the benefit of both sides of your disc. So because it's a capacitor, and you'll find that as you get into it, because it's a capacitor, because I've stacked it, I've got one underneath and I've got one on top, so I'm using both sides of both things, and that gives me an advantage, right? Makes it easier to get your capacitance up and multi-stack it. I've just done this as a demo model that anyone in the world can download and recreate, and it'll work. You don't have to do too much to it. Just do it the way it's done and you'll be right. Moving on. Righto, still on electrostatics. This one here. This guy is pretty good. I was lucky enough to get, I think this was the last book that they had on print, whether they've run another print of it or not. It's not cheap. I believe there's a PDF download. I think I got the PDF download first. There's another mob called forgottenbooks.org. This one, I wonder who don't know, it doesn't say who the publisher is. But anyway, just this one here, modern high-speed influence machines, right? Now that was written, I think it was written nearly 100 years ago, so even though he says it's modern, I wouldn't put too much into it. But this guy is good. Like when you read this book, you'll understand. He goes through a lot of different, and he gives an insight into how to really enlarge that machine. He pressurizes his stuff. We're not doing that because it makes it too hard. But at the end of this video, I'm going to show you on paper how we can multiply this machine out to make it far better than what it is. Moving on, so that's mainly the statics, the high voltage side of it. So it's 50,000 volts or more. It could, you really want to get up into a couple 100,000. But anyway, those three books will give you tips and tricks on it. Moving on. This one here, so all of Tesla's books are worth getting, but this one's very good too. And this is high potential, which is what we're dealing with, and high frequency. We're not doing high frequencies, but that one, it just gives you a bit of an idea. Actually, I think I'm picking up the wrong book there, and I'll show you later on. This book here, it's not a very big book. It's not very expensive. You can get it. You can get a download of this. This book here will teach you, has got all the information you require to transform this power and transmit it. So you can transmit it around the room, recharge your phones, whatever you want to do. Here's your radio hookups. Cheap little book. You can buy 100 radio hookups. So this is all back in the day. This is how they did it. You don't need a battery or anything for your receiver, but you're transmitting. It's all similar, but Tesla, you can't go past Tesla, right? You cannot go past this book. This is a must, because this Tesla's dealing in I'll show you the patent. It's in here. This here. This is pretty much what I've built so far. It's not exactly the same, but there's the generator there. It's going through a transformer, and there's your outputs, right? So anyway, it's in there. All the information you need is in that book. All right. Now, there's a motor on this. The motor on this you won't find anywhere. Here it is here. Robert Adams, a nice bloke, a New Zealand guy. He took it all a bit too personally. If he had just ignore everyone else and just keep doing the job, mate. Don't get bogged down in it all. He got bogged down in it all. He took it all personally and all this sort of stuff. I mean, I'm lucky I don't have any credentials, so no one can really, I don't care what people say. Here it is here. It wasn't very expensive. I got it off Nexus. So Duncan at Nexus, they're up on the Sunshine Coast in Australia, but whether he's got a download on the internet now, you can download the PDF or something, I don't know. But it helps to explain that motor. Righto, we've hit our time for that. So here we go, we're going to quickly run through these ones. This book here, righto, so when you read books, I don't know how old you are, whoever's watching this. Now, I'm going to tell you something about a book. When you read a book, the way a book is written will tell you if the person wrote it, if someone else wrote it, And when you read it, you should be able to, the person, you should be able to pretty much be sitting in the chair as they're writing it. So when he does a book like this, My Inventions and Other Writings by Nikola Tesla. Now, introduction by someone else. This should be a reprint of his exact words, right? So when you read a book that says My Inventions and Other Writings, by any of his books that say that, right? I'll give you an example. This one here, this is a good book too. I've got no complaints about it, but it's not written by Tesla, right? So some of these are, some of these aren't. Some of these are excerpts of his, of what he's written, and then some of them, when you read it, you go, that's not right. And what it is I think it's someone sitting in his lecture and taking notes. And when they've taken notes, whether they're doing it in shorthand to keep up with him, so whether they actually work it out or not, whether they've made a mistake in what he's saying. Here it is here. This is what, and this put me off the scent for like 5 years. I wanted to build this machine at least 5 years ago, and when I read this, I walked away from it, and I thought, and it's all because of the last line here. It says, the effects, however, cannot be compared with those obtainable with an induction coil, which is operated by an alternate current machine of high frequency, some of which were described by me a short while ago. Right, but he could be running a big diesel engine to drive that. We're just trying to make an efficient generator. My thought is, because I'm a machinery operator and all that sort of thing, my thought is, if you were to, with us, we pay, I get a fuel bill. When I'm operating, I had Bobcats and trucks and all that, I get a fuel bill every month, $200 or $300 a month. Whenever I go to buy a machine or anything to do with machinery, I'm always looking for a cost-effective machine to run. If I'm going to put $5 worth of fuel in a machine, I need to be putting it in a machine that's going to produce more than what some other guy's machine that's not right is going to produce. Anyway, we'll keep moving on. These are real quick. I'm going to go through these real quick because I've already gone through my time. Let's start with Jeff Menko. This guy's really good. He gives you a lot of, this particular book here, I'll put it there, right? This particular book here is electrostatic motors. This variable capacitor that we've made here, this middle section, it is not a motor, so you can go through that book and see it, but he's a really nice bloke. He's done a great job Another great bloke who's done a great job. So that's that. We'll put that there. There's another copy of that A.D. Moore's book. That's really good. Right, here's Jeff Menko again. He gets, this is one he ties it all in with gravity. It's pretty good. A lot of formulas. Don't get bogged down in formulas. If someone tries to bog you down in formulas, don't bother. The only one we really need for this is the capacitance formula. It's only a few letters, so it's not that big. Righto. Induction coils. This is pretty good too. It gives you a bit of it gives you some calculations in the back on how to calculate the coils and everything. The coils that I wound in here, right? My coil, here's one of my coils. This is a small version for a different motor that I made, right? And this is important. Do not be lazy. In this book, they will tell you to wind this way and then wind back and wind this way and wind back and wind this way. Right, don't do that. I've made this so you can pull it apart, you print that, you glue it onto this roll pin. This is a 10mm roll pin. And your wire feeds through the middle. There's a gap in there so that your wire will feed through. Anyway, your wire feeds through. So you wind it on. Here's my wire here. You run out 20 meters of wire. Wind 7 layers. You could wind 8 or 9 if you wanted, but I wind at least 7. Then cut it off. However much you cut off, when you do your next one, you know, go an extra half a meter, but don't go 20 meters. Go whatever it is, deduct the bit off. Anyway, you wind it on. You get your 20 meters. You feed it to whatever's left. You feed it through the hole that is in there. There's a little hole there somewhere, right? You can feed it through that hole. You wrap it over one of these notches at the other end so it doesn't move, and then you wind it on again. Hang on. And then someone trying to call me. Anyway. Right, don't be lazy. Take the time and effort to do that properly. And you can see here at the end, you should have your little, see it tied it over the end there? Little holes and all that. You just want to keep them neat. It keeps them neat. It keeps all the power flow. This book will explain why not to wind back. It creates capacitance, resistance in your coil. Anyway, another good book, lostbooks.com. Very truly yours. Tesla and a few of the other guys, Thompson, had arguments in the day, back in the day, so it's really interesting. Again, Tesla, all of Tesla's. This one here is really interesting, and this is the problem we have now. So he predicted it 100 years ago, and here we are with that problem. This one here, I think, was the book that I meant to mention to you before, Alternating Motors and Currents and all that sort of thing. That's a good book too. And I believe in here you will find... No. Anyway, there's a patent. The patent's up there on the wall. I will put that patent in so you can see how to transform the power. Here's a classic example. This wasn't written by Tesla. This is someone else has written this. They've gone through and gathered his stuff and put it together in their own format. So, you know, if it's not his, if it's not the true author's, be wary of what you're spending money on. Here's some more books. Right, so again, maybe, you know, some of them are alright. They're just good references. This is written by David Hatcher-Childress, isn't it? David Hatcher-Childress. He's pretty good, Dave. But, you know, again, he's gone through, there's your patents there. So this is all it in here. How to transform this power. Again, Colorado Springs notes. So they're all pretty good, but those first books are the main ones you should be dealing with. A book like this is good too. Right, now the problem is you don't want to get bogged down in it. I use this book for a reference. It's just 600 pages. What annoys me, out of the 600 pages, only 2 pages are dedicated to how to make electricity, 598 pages how to use it. So, and the 2 pages in this book, how to make electricity, have got nothing to do with that generator there. So you won't find anything in there on this. I'll get to them later if we have time. We're running out of time, I can't believe it. Anyway, righto, in the links, I've put in 2 good links. One of them is Dr. Antonio. He's done a lot of work on static electric machines. And the other one is Professor Walter Lewin. He was good enough to put up his physics course, and in particular mentioned there's number 7 that deals with capacitance, which is what we've got here. This is what this section here is, our capacitor module. He does capacitance, right? And in that, he will go through what happens when you change the formula of capacitance. Capacitance formula is C equals epsilon 0 multiplied by the area divided by the distance between the plates. Now, he goes through, he has Q free, so he allows charges. We've got 2 Q free, we've got 1 Q free and 1 un-Q free, right? So we've got, when you look at his thing, you'll notice that the rotor in here has got trapped charges. The charges are trapped on it, they can't leave. The other corresponding, so here's our rotor, it's got trapped charges. Our plates don't have trapped charges, so they're Q free, right? So this is Q, just Q trapped. This is Q free. It can go from this side. I haven't done the other side, I've just done it so that you can see that this side is 1. I'll show you on this. So as this turns, I'll do it that way, maybe see it better. As it turns, it overlaps both of them, and then it turns. Oops, and then it turns, and they're not overlapped. And it turns again, and they're overlapped. So what it's doing is, when they're overlapped, if this is charged, I don't know what's charged. So if this is charged at 50,000 volts, it will induce a charge on this of the opposite polarity of 50,000 volts. That's basics of it. Professor Walter Lewin's class will get you further into it. Now, when you do the class, you'll notice you also do magnetism. So there's 2 parts to this. There's 3 generators here. The top one's a generator, the middle one's a generator, the bottom one's a generator. The bottom one I'm running is a motor, but it's also, within itself, it's a generator. When you put it on the oscilloscope, you'll see why. This is the magnet. So when you do, I'll bring you a little bit closer now. When you do the class, sit through these classes, you're going to see the B field. The B field, and you'll notice that all that they have arrows and that, this is the direction of the B field. What they don't do is they don't do geometry, right? So you can build geometry into your system. Oops. You can build geometry into a system simply by changing the geometry. When you do the class, the B field, the ion becomes saturated, and that's it. There's no, you can't get anything here, so go away. But when you actually work with it in the real world, you can build geometry into your systems, and you can look. You can't even roll this thing back the other way. Look, why? Geometry. It's not in the class, so that's fine. Improvements. Geometry. Righto. Right now, let's get serious. Geometry is hard to achieve with a magnet. Geometry is not so hard to achieve with statics. That's why I did this, is because with static, when you do Walter Lewin's stuff, you'll see that they have 3 Gaussian surfaces: a sphere, a cylinder, a flat plane. We're using a flat plane. A sphere, it's pushing out all around it. A cylinder is pushing out all around it, all the way along the length. A flat plane, the force, perpendicularitis they call it, but anyway, here's the force that's acting on this. The reason why the force is perpendicular, if we took one little square there, the force is going straight up, because the one right beside it is going straight up. So the one beside it is holding that one up. It can't bend over because the one beside it's pushing it up. So, and you'll see it when you get statically charged, the hairs on your arm will all stand straight up because they can't push over the one beside them. You just become charged. They're all trying to push apart from each other. They can, so when you've got a flat surface, there is a trick here. This flat surface, so there is a problem. You do have an edge. We're in a 3-dimensional world. This is an edge along here. Oh, I'll show you this way. Here we go. I'll try and do it like that. So each just here. So see these 2 are here, right? There's an edge here and there's an edge here. So what's going to happen is we're using, if you use your spark gap and you have a little spark there, this capacitor plate will never fully discharge, and it'll probably never fully discharge properly if you don't have a spark gap. But anyway, let's just focus on the spark gap. If you have a spark gap, You're going to leave residual charge on your plates of a couple of thousand volts. So what's going to happen as this moves towards it, if it's moving in this direction, it's going to see that charge on the edge. So this edge here and this edge here are going to attract each other, and it's going to move towards it. But what if it was moving the other way? What if it was moving like this and was moving the other way? It's moving the other way, it's moving the other way, bang. That same charge is going to attract that and try and slow it down, right? So there is your resistance on this system. You have one side trying to pull it in, you have one side trying to pull it back. They sort of balance each other out. I won't get into it. It's not really my place. Right, so improvements, how to improve this machine. This is the main reason why I did this video, because I made a few mistakes. Whenever you're making something like this, the best way to do, because I had to make everything, it's very hard to get your head around the imperfections. I just had to make something. I thought, oh, if it's a mistake, I can come back. Let's just make it and get it together and get it going and then come back and fix it. So here's the fixes. When you do the Walter Lewins thing, you'll realize D is a big factor. This plate is when I did it, it's 3 millimeters thick. When I did this one, it's 3 millimeters thick. So the distance between these, if I bring it over a bit closer, the distance between these is 12 millimeters. So if these are sitting on average half apart, the distance between them is going to be 6 or 7 millimeters. What I've done it here, there's a hole here in the bottom. What I was supposed to do was come out and cover this surface area as well on the bottom. So bottom and top. So I've got to put a little hole in this one so you can get through to the other side. Would halve the distance between them. So I'm going to run through the calculations with you. We're going to call the output of this machine, I had a pen and now I've lost it. We're going to call the output of this machine O. We're going to, by changing our distance, we're going to double our output. O multiplied by 2, right, equals 2O. The other day, what I did was, I was running this at 11 volts and I was getting 45 to 50 RPM. Now I'm running it at, now I'm running it at 19 volts and I'm getting 92 to 95 RPM. So that's another 2 times the output. The way that this thing works is I just showed you by turning it, but every time that clicks, if we can put it there so you can see it. So every time that clicks over, right, bang, that has to discharge and it has to charge the other side. Every click, so 4 turns, 4 discharges, 4 recharges. One cycle is 4 discharges, 4 recharges. So if I double the amount of cycles that I do per revolution, per hertz per second, because it's doing 90 clicks a second now, where before it was doing 40 clicks a second. That's a click. If we call that a click, we call every time it does that a click, click. It does 90 of them a second, so that's going to double the output. So now we've got 4 times O, so times 2 times that, times 2O equals 4O. Then if we doubled our, say we tripled our sectors, I was going to do it anyway. The problem is not on this. This will always, so your sectors on your rotor will always take up 50%, exactly 50% of your rotor. The sectors on your plate won't, because you have to have a gap between the two. If you didn't have a gap, the gap is equivalent to the size of the spark you're going to get. If you don't have a gap between these two plates, it's just going to arc out in here and it's not going to give you a spark gap over there. That's why you're a bit limited on the spark gap here, is because you're going to get breakdown across your plates in here, and it doesn't need to run out through the wire across the spark gap to come in the other side. It can just break down internally. If we increased our, without getting too far into it, we could triple our sectors. Right, so instead of having 4, we could have 12 sectors. So on a bigger machine, I'm just talking about a bigger machine, not talking about necessarily this machine. So if we had a bigger one, we'd have 3 times 4O, which equals 12O. The other thing was the area of the plate. So if we made a bigger machine, here it is here, I've measured it. This is the size of the disc we're running off a 200mm build plate, and they're only 150mm, these things. If you could get a 300mm disc, right, the surface area difference is more than triple. It's nearly quadruple. It's 174 as it is, and it could go up to 702. So it's nearly triple. It's more than triple. So we're just going to use triple. So you got to know that. So if we did that, we did a bigger disc, we'd have 3 times 12O, which equals 36O. Then the other thing is these rods come in a 1 meter length, so we can go 1 meter, which would give us 2 more stacks. This stack here is only 200 millimeters, so 2 more stacks would be 400 millimeters. This is not even 600 millimeters high, so you'd fit 2 more stacks in there. So that's another 3 times. So we're going to go 3 times 36O equals 108 times O output. So we can get 108 times the output out of a machine like this if I didn't cut down my rods and I had to use a 300mm disc. And I double-sided them. Now, there's one last topic that could improve this greatly, and it's too hard to put a figure on. I'll give you an example why. When you go through all this stuff, dielectric is a pretty big part of it, and the dielectrics that I used are, I first off used this one, and I think this sort of thing is good. No air bubbles. I went with this, basically said with this one, I just went on the internet and this came up and said it'll stick to anything. It'll stick to plastic, it'll stick to metal, and that's what I've got, metal and plastic. So I went with it, I ordered it in. It's just a high gloss, and I just gave it a couple of coats. The problem is that I'm having is when you cut with a knife, you sort of can't see, you cut twice. If you leave one piece of tin sticking up, the voltage on that, if you got 40,000 on your plates, the voltage on that one piece of tin could be 200,000 volts. It just burns a hole through your, and it'll all be explained in A.D. Moore's book. So you've got to, I'm thinking about going to the paint. This is pretty good paint. It's paint on, so I was thinking about doing metal in the middle and then paint on around the edges. Right, so it doesn't matter if you got a rough bit in here, it's only around the edge. The edge, the voltage on your edges is going to be huge compared to the voltage on the center of the plate. It's all explained in the books that you're going to read and Walter Lewin's thing. And that's about it. Quickly, there is some other books here. You can get into a lot of books. I got heaps of books down the back. I don't mind books because I can read them real quick. I don't get bogged down. Don't get bogged down in it, man. Just move on. If you don't understand it, move on, because the next page will probably explain the last page a lot better. You can get into all sorts of things there. We haven't got time for that, so we might do it some other time. And that's about it.